All right, so for this lab report, which is the gaseous equilibrium lab report, I want three things. One, I would like the report form completed. Two, I would like all of your calculations associated with it. And then the last page, the copy of the data. And so ultimately, we're going to jump right in and we're going to talk about the data that we collected. So to start with, I'm going to show you that the data that I collected is right here. And so I have a temperature at 20 degrees and an absorbance at 0.21. That's my room temperature. So I'm going to note that really briefly. That's my room temperature data. And then I've got another temperature at 41 degrees and an absorbance at 0.26. That's going to be your hot temperature or your heated. So I'm going to note that as HT. And then when you've got your cold temperature, and yours is going to be slightly different, but mine is at 2.2, and I found an absorbance at 0.7. And we're going to call that our cold temperature. So I'm just going to put a CT next to it. So to begin with, we're going to start by looking at the data at room temperature, because ultimately our system is at equilibrium at room temperature. So we've got to figure out what are those concentrations of NO2 and N2O4, because this is our reaction, that they're at equilibrium at room temperature, and what are those concentrations. So to find that, we're actually going to use this equation right here, which is absorbance A is equal to epsilon, which is the actual molar absorptivity coefficient, times B, the path length, times C, the concentration. So we're going to be looking for that concentration. So we're going to start there with A equals epsilon BC, and we're going to start this by finding out what is the molar density of NO2. So to find that, we're going to take this room temperature data. That's our goal, is to find out what are going to be those concentrations that we begin with before we shift the equilibrium by heating or cooling the solution, or rather the gas mixture. And so when we start this, we have absorbance of 0.21 is equal to epsilon, and this was from your lab information in the procedure, and we find out that that's a constant that ends up being 2.95 times 10 to the second liters per mole centimeter. And that we just found from the procedural information. Times B, which is 1.00 times C, the concentration. So we can find the concentration of NO2. And the reason we can find that is that absorbance that you saw is directly related or directly correlated with the amount of NO2, which is your brown gas, that is absorbed. So we can find that concentration of NO2, and when I do that math, I find 0.00071 molar. So now we know what our concentration of NO2 was to begin with. So that's step one. But we still need to know what was the concentration of N2O4 also at room temperature. And to find that, we're going to look for what we will call as the molar density of N2O4. And in order to do that, we're going to look at K, our equilibrium expression, which ends up being the pressure of N2O4, which is what we're looking for, or rather I should say concentration, because we're looking at these in terms of concentration units. So concentration of N2O4 all over the concentration of NO2 squared. Now when you look at the chart that's in your procedure, you're going to find out what the K value is from the table that's closest to your temperature. So at room temperature, mine was roughly 20 degrees Celsius. If yours was 22 degrees Celsius, you'll look for the K in the chart that's the closest to that in the procedure. But for mine, it was 20, and I found K was equal to 248. And then what I'm going to do is I'm going to plug in the concentration at room temperature for NO2, which we determined from A equals epsilon BC. And that concentration was 0.00071 molar squared. And we can then find the concentration of N2O4. And when I do that math, I find 0.00013. Let me make that so you can see it a little better. Whoop. Molar. So now we have the concentration of N2O4 and the concentration of NO2 at room temperature. But then we put a stress on the system. And the stress that we put on the system, so I'm going to sort of block this off a little bit. And I'm going to make a note. We put a stress on the system, or on the reaction, and that stress was we increased the temperature by putting it in a hot bath, or we increased the heat. And we've got to think about Le Chatelier's principle. So we've got the reaction, 2NO2 yields N2O4. It was at equilibrium, and then we stressed it. Now Le Chatelier indicates that there will be a counteraction to that stress, and thereby it will decrease the heat. And remember, if it decreases the heat, it's wanting to consume the heat in order to get back to equilibrium. So we've got to figure out, is this an endothermic or exothermic reaction? And if you look at your procedure, it tells you that it's exothermic. And so as a result, that means that heat is a product. So since heat's a product and it wants to consume heat, it's going to move away from heat. So this reaction will shift to the reactants, or shift left. So that tells us what the change will take place in order to get to equilibrium. And that change, telling us it shifts left, tells us that it will consume N2O4 and make NO2. Hence the minus X because it's consuming, plus 2X because it's producing NO2. And that's why you had that more brownish color in there than when you started. Now the initial concentrations before we stressed it come from above. So notice the NO2 ends up being 0.00071, and the N2O4 ends up being 0.00013. And then that tells us that at equilibrium, since the sum of those two rows in the similar columns ends up being what's happening at equilibrium, we would have plus 2x here, and we would have 0.00013 minus x. So we've got to figure out something about equilibrium in order to figure out what the K value is, because our goal is we found out what the molar concentrations were initially at room temperature, but what we want to find out from this second part is we want to know what is the actual K value once we make the shift to a new temperature. We want to find out what is the K now that we're at 41.1 degrees Celsius, since that's my hot tube's temperatures. Yours may be 50 degrees Celsius, it may be 52 degrees Celsius, but either way, we're both still looking for what is K at that temperature. So we've got to figure out something about the equilibrium information. And the good thing is, we have up here in our chart an absorbance that occurred at that hot temperature. For me, that was 0.26, so I can plug that into my A equals EBC, and I can find out what the concentration of NO2 was at equilibrium. So 0.26, that's my absorbance from my hot tube, equals 2.95 times 10 squared liters per mole centimeter times 1 times C. And this is going to give me the concentration of NO2 at equilibrium in the hot tube or the hot temperature. And I ended up finding that the concentration of NO2 ends up being 0.00088 molar. So what's also true is that this value right here is equal to 0.00088. And so I can take that information, and I'm going to switch back to black so you can see it a little better. And I can take that 0.00071 plus 2x is equal to 0.00088, and I can solve for x. And when I solve for x, I find 0.000085. And I can plug this value now. I'm going to go to highlighting it again. Now that I have x, I can plug it into here and find out what my N2O4 is equal to. So I'm going to plug that in here and find my N2O4, and I found it to be 0.000045. And lo and behold, now that I have equilibrium concentrations of both NO2 and N2O4, I can now go back to my K variable, which we had earlier. And remember, it's products of reactants. So I would take my K, and I would take my N2O4 at equilibrium, that concentration, 0.000045, and I would divide it by the equilibrium concentration of my NO2, which we determined from the concentration over here from A equals EBC, 0.00088, and remember, since there's a 2 coefficient in front, that would be squared. And we can find out what that K should be equal to in terms of that hot tube. So the K at 41.1 ends up being 58, which makes sense because we have fewer products since it shifted towards NO2, and so my K should decrease. Now, when we look at the second tube, and I'm going to get rid of some of this information down here, so let's get rid of some of this. We're going to do a similar thing for the cold tube that we did for the hot tube. The difference is we have to think about the shift with respect to the cold tube. So think about that. We now are in the cold tube, and so we're going to come back up here, and our cold tube is at 2.2 degrees Celsius, and we have an absorbance associated with that. So we're going to come down here and think about what's going on. The first thing is the stress. So cold means that we have decreased the temperature, or we've decreased the heat. So what's going to happen if we decrease the heat? Well, Le Chatelier says that's okay. It's going to shift back towards equilibrium, so it's going to increase the heat. And when it increases the heat, remember, this is exothermic, so it's going to shift and make more heat. And so if it makes more heat, it's going to shift to the right and make more products. So that means over here that now we have plus x because we're making more products and minus 2x because we're consuming the reactants to get there. So the signs change here. And then you would continue forward just like you were before, where we figure out what is the actual equilibrium concentration here. And that, in order to do that, we would end up using the absorbance associated with the cold tube. So we would come down and bring 0.17 is equal to 2.95 times 10 squared times 1.00 times C. And then once we found that concentration, that's my concentration of NO2 at equilibrium in the cold temperature, or at the cold temperature. And that value is going to be equal to the sum of 1.0071 minus 2x. And then you can move forward from there like previously, and then find your new K based at this temperature, which should be larger in this case because it's shifting to make more products.